When we were proving a pair of triangles congruent, we went over 5 postulates and theorems to do that. Now we are proving that a pair of triangles are similar. The good news is that there are only 3 ways to do that. This is the first of those ways. Back when we did prove triangles congruent, it is very common for students to try and make AAA one of the ways to prove them congruent. It doesn't work for congruent, but it does work for similar. This is that postulate. If 2 angles of one triangle are congruent to 2 angles of another triangle, then the triangles are similar. That's it. It's pretty simple. All you have to do is match 2 angles and you're done. This postulate name is way too long, but the good news is that there is a commonly agreed upon abbreviation for it. All you have to do is write this. Don't forget the tilde at the end. Why isn't it called the AAA similarity postulate? Students often ask that. The answer is that we don't need to. 2 angles is all we need, and Lord knows, if we can save writing a letter, we will. In the triangles below, once you know 2 angles of one triangle are congruent to 2 angles of another triangle, then the third angles must be congruent too. Do you remember the theorem that covered that? It was the third angles theorem from way back in section 4.1. Anyways, 2 angles is all that you need, so that's why it's AA similarity and not AAA similarity. Other than that, there isn't much else to say about this postulate. Just match up 2 angles and you're done. You've proven the triangles are similar. This next one is going to look kind of similar. Congruent triangles had their SAS postulate, and similar triangles have their SAS similarity theorem. They are related, but do work a little differently. First, the official theorem description. If an angle of one triangle is congruent to an angle of a second triangle, and the sides that include the 2 angles are proportional, then the triangles are similar. That isn't the clearest definition, so I'll try to explain it a bit better. First, we need some triangles, though. With similar triangles, sides are proportional, but the angles are congruent. So let's start with the angle since it's easier. All we have to do is show it's congruent. If we want to use SAS similarity, then we have to have one angle matched up in both triangles. Let's assume I have these 2 angles congruent. Now what about those sides? When we did the SAS postulate with congruent triangles, we matched up a side, an angle, and a side, which was easy, but we also had to make sure that the angle was in between the 2 sides. That's why it's called SAS with the A in between. That's the same thing here. The parts must come in the right order. The angle must be in between the 2 sides we use. Since the angle must come in between the sides we use, then we must be using these 2 sides. Now we have the right parts. 2 sides with the angle between them. But what do we do about those sides? When we did congruent triangles, we just showed that they were congruent. Here we have to show they are proportional. To do that, we have to show this proportion is true. Both of them should reduce down to the same thing, which will be the scale factor of the triangles. That's the one little difference to the SAS we had before. Like the AA similarity postulate, this theorem has a common abbreviation. Be careful though. I warned you with the AA similarity postulate, but it is even more important here. You must remember to write down the tilde. If you don't, then you are using the congruent postulate from section 4.2 and saying that the triangles are congruent. Don't forget the tilde. Other than that, you probably have a good sense of how this theorem works. The last one is the side-side-side similarity theorem. Without even going on, you may already know how this one will work, but I suppose I should show you anyway. First, the official definition. If the corresponding sides of 2 triangles are proportional, then the triangles are similar. Just like SSS from chapter 4, you have to match all 3 sides of one triangle to all 3 sides of another triangle. The difference is we have to show them proportional here instead of congruent. Here are a couple of triangles to work with. I already have color-coded the corresponding sides. In order to show that the 3 sides are all proportional, I need to show that this extended proportion works. You must show all 3. 2 of them is not enough. Some students quit when they see 2 of them will work out, but you aren't that lazy, right? You do actually have to verify the 3rd side is proportional also. Like the other ones, this has an abbreviation. And like the other ones, you must remember to include the tilde, or you are saying the triangles are congruent instead of similar. With SSS similarity, you might end up with problems that don't even have a picture like this one. You need to try and figure out if 2 triangles are similar, and you do have the side lengths. To figure out if SSS similarity works, you need to match up the corresponding sides. Given this situation, some students naturally want to try and sketch out the picture to find the corresponding sides, but that isn't actually the way to go. What should we do instead? What you should do is you should always match up the smallest side to the smallest side, the medium side to the medium side, and finally the largest side to the largest side. This is the way to go. This is by far the easiest way to approach this problem. Well, assuming you can find the smallest of 3 numbers, I suppose. In this case, the 2 smallest sides are 16 to 4, the 2 medium sides are 20 to 5, and the 2 largest sides are 28 to 7. All of them reduced down to 4 to 1, So the sides are all in proportion. So these triangles are similar due to the SSS similarity theorem. And we didn't even need a picture. Just always remember, match smallest to smallest, medium to medium, and largest to largest, and you will be okay.